Hello. Sorry about my voice. I have a rather bad cold, so that's how it is. Anyhow, this will be about electrical power. So we have power, and that's equal to, we write that as P, and that's equal to how much energy we use per time unit. So the more energy per time unit, the higher the power is. And the unit for that will then be joules per second. But what is the unit for this? Actually, that is a bit bad joke because the shortened form for the unit would be watts, that we write as a W. And you can see this in many stuff. You can see how much power you need to make a lamp shine, or what power output you have from a charger and so on. And we'll look at a few of these cases. We can do an interesting modification of this formula, because if you think about it, we have one formula including energy already, and that is that our voltage is defined as energy per charge, which means that we could write energy equals to voltage times charge. But if we plug that into the formula we have here, so we take this here, plug that into this one, we get that power equals to voltage times Q divided by T. But wait a minute, Q over T, we should recognize that, right? We have the definition of current equals to Q over T. So we can take this and replace it into here, and we get that power equals to voltage times current. And that is the form we will basically use it in. And it makes sense, right? The higher voltage you have, the more energy per charge, the more power you can transmit. The higher current you have, the more electrons that move, the higher power you can transmit. So hopefully that formula makes some sense. Let's try to use this formula now. Say we have a lamp connected to the mains electricity. So that would be here 240 volts. And we have a current here of 150 milliamps. And the question is now, what power will this lamp have? Or rather, what power will it dissipate? To dissipate power means basically the power that comes in that then turn to, say, light and heat. So if we try this, we see that the power equals to V times I, and V here is 240 times our current, that is 0.150. Okay, so let's take our calculator here, and we do 240 times 0.150. Oh, we get 36 watts. So our lamp will use 36 watts. So that is 36 joules per second to shine. Okay, over to another case. Here we have a charger for a mobile phone. I'll just draw that as a block here. And yet again, we have mains voltage, 240 volts coming in. And we say that this is rated at 50 watts. And our question is, what current would we have coming in here? Okay, so we have that power equals voltage times current, which means that our current equals to our power divided by our voltage. And the power was 50 divided by voltage, that was 240. So let's grab the calculator again. So we have 50 divided by 240, and that is gives us 208 milliamps, so rounded to significant figures, 210 milliamps. Okay, so equals to 210 milliamps. Okay, now out from this, the charger has turned this 240 volts to 5 volts. And assuming we have no losses here, so we still have 50 watts out, then what current will you have here? Yet again, we can use the same formula here, that I equals to power divided by voltage. In this case, the power yet again was 50 divided by voltage, 5 equals to 10 amps. So we have turned high voltage, low current to low voltage, high current. And that must be so if the power should be the same. Now we say that this should charge a phone which has a battery that has a charge of, say, 4,500 milliamp hours. Now remember this, that current equal to charge over time. So in other words, charge equals to current times time. And that is actually what we have here. 4,500 milliamps times the time, 1 hour. We can use this formula here to make T our subject. So T equals to Q over I, right? So we plug in our numbers, and now we'll write with units, which normally we don't do in formulas, but it makes more sense in this case. So 4,500 milliamps hour will be the same as 4.5 amp hours, since milli means thousands, so you move decimal point 1, 2, 3 steps. So 4.5 amp hours. Good. So that will give us 4.5 amp hours divided by our current, that was 10 amps. Amp and amp will cancel, so that will give us 4.5 over 10 hours, or 0.45 hours. And you can multiply that by 60, so 0.45 times 60, we get a charging time of 27 minutes. I don't know if my face will cover that, so right, equals 27 minutes down here. And we have solved the problem. So in other words, with a current of 10 amps, it would take 27 minutes to fully charge the battery. And that is with a 50 watt charger. So let's look at another example. Say we have a battery, 12 volts, over a resistor. I'll say that resistor is 50 ohms. And we should figure out the power dissipated or used, so to speak, turned to heat in the resistor. So to do that, we need to find the current. And we have resistance equals to voltage over current, or in other words, current equals to voltage over resistance. The voltage was 12 divided by 50, right? Either two. Okay, so let's calculate that. 12 divided by 50, and that will give us 0.24 amps. And then we can calculate the power equals to voltage times current equals to 12 times 0.24. And what we get here, we can take this times 12. Observe that when I just pressed times, it automatically fill in the ANS thing there. And we get 2.88 or 2.9 watts. But we could do this in a nicer way. Write the formula again here. Power equals to voltage times current. But we can see up here that we can replace I by V over R. So we get V times V over R, or V square over R. Let's fill in the numbers. V is 12 square over resistance 50. Okay, so let's try that. V square 12 square divided by 50, and we get the 2.9 watts again. And this by itself, power equals to V square over R, can also be a very useful formula. Now let's look at another example. Instead, now we have battery. We don't know the voltage, and we have a resistor here, and say we have the 50 ohm again. But in this case, we have a current of 0.50 amps. And yet again, we should calculate the power. So now we need to find the voltage again. But we have R equals to V over I. In other words, voltage is R times I. R is 50. I is 0.50. And that will give us 25 volts, right? Because times 0.5 is just half of it. So we take the power again here, equals to V times I equals the voltage that now we know is 25 times the current, that is 0.5, that is half of 25, and that is 12.5 watts. I know that this is 3 significant figures, but the problem is with 12.5. I should round it. Technically speaking, we should round it to 12, but I keep it as this. Anyhow, we can do a similar trick as before. We write P equals to V times I, but now we have a formula here for V instead. So we plug that into here. So that will be R times I is RI square. So what will that give us? P R times I square. R was 50 times 0.5 square. Okay, let's try that. 50 times 0.5 square, and we get the 12.5 back again. I write it down here. Equals 12.5 watts. And yet again, we have a nice formula, but power equals to R times I square, which in itself can be quite a useful formula. So, hope this helps. Thanks.